Alrighty, in this video, we're talking about superposition and source transforms. Let's start with the source transform bit. If you remember DC, I had a relationship between a voltage source with series resistor and a current source with parallel resistor. We're doing the exact same thing in the phasor domain, except we have impedances instead of resistors. So I know that Vs, looking like this, phasor with a Z phasor source in series, can be converted back and forth with a current source Is in parallel with Zs. And the relationship between these is as such: Vs is equal to Is times Zs, which means that Is is Vs over Zs. I don't know why I keep writing 2's instead of s's there. And I know that Zs is the same in both situations. Alright, so I know that I can use source transforms the same way as I did in DC. The other thing to note before we launch into any sort of example here is to talk about super soakers. By the way, have you been to a store like Walmart anytime recently and looked for super soakers? Those were kind of like a staple as I was growing up, and I have been literally unable to find them anywhere, which was a real shame. I was trying to get a gift for a friend's kid for his birthday, and literally no super soakers. I guess his parents are probably stoked about that, but I'm a little bit disappointed. Anyhow, superposition. Alright, so we're applying superposition exactly the same as DC, except if the sources have different omegas, then the phasor transform is different for the circuit. Right? The impedances depend on the value of omega. So if I'm going from time domain to frequency domain, that doesn't work unless all the frequencies are the same. But in this case, those frequencies, if I use superposition, I turn off all but one sources, then I can make all the frequencies the same and do that. And then the last little caveat with that is when I go back to the time domain, I add them together as sinusoids of different frequency. I cannot just simply add them together. One does not simply add together the phasors that we get doing superposition. That's a big no-no because the omegas which made those phasor results are wrong. So one does just not simply walk into Mordor or something, whatever the meme is with that. As if I don't know. Alright, so let's do an actual example of this. Example number 1. I've got a source which is 10 cosine of 2t volts with a inductor. It's 2 henries. Beautiful, beautiful inductor there. You can definitely tell I am a gifted artist, gentleman, and scholar. I've got 2 sine of 5t amps. On that current source, I've got a resistor, which is 1 ohms, and I'm defining my voltage V0 across there. I've got a capacitor, which is 0.1 farad, and then I've got 4 ohms here with a 5 volt DC source. So this is 5 volts. Omega here is equal to 0. And I want to find V0 of t. So V0 of t is equal to V1 of t plus V2 of t plus v3 of t, not just their simple phasor addition. If you do that, you will be wrong. In so many ways, and if you happen to see that on any sort of exam, your faculty member is going to mark you wrong 5 ways to Sunday. All right, so let's start with V1. To find V1 of t, I actually want to start by turning off all but the 5 volt DC source. When I do that, omega is 0, so j omega L is just equal to 0, and 1 over j omega C is just equal to infinity. And so what that means is that our capacitors look open and our inductors look like shorts. And turning off a voltage source is a wire, turning off a current source is an open, and so I'm left with something that looks very much like this. I've got my 1 ohm resistor here, my 4 ohm resistor there. I've got my voltage source over here, 5 volts. And then I've got plus minus V1. This could be in phasor or time domain. It does not particularly matter with this exact one because it's a DC voltage. So V1 using voltage division is negative. Negative because the plus sign of my source is up here. It's going into the negative sign of V1. So negative 1 over 4 plus 1 times 5 looks a whole lot like negative 1 volts. Next, we'll move to finding V2 of t. I'm going to turn off all but the voltage source on the left-hand side, the 10 cosine of 2t volt source. And what I'll do is I'll do the phasor transform here. So I've got 0.1 farad. That becomes 1 over j times 2 times 0.1. Which is the same as 1 over j.2 or minus j5 ohms. 2 Henry transforms j omega L, transforms to j2 times 2, which is equal to j4 ohms. And let's see, 10 cosine of 2t is going to transform to 10 angle 0 degrees volts. Now I'm totally going to remind you here, it's really important, that because I have done it this way, this phasor form of that voltage no longer preserves the frequency information, which is why I can't just add my phasor results together. I have to add the time domain results together. So here we go. If you can't tell, I have had my fair share of coffee before the recording of this video. I am sure some of you are just totally shocked to hear that, since I am not at all excitable or interested in delivering this with a lot of energy or anything. All right, I've got 4 ohms, I've got negative J5, I've got 1, my voltage in the phasor domain, V2, is defined across my 1. I've got J4 there. I again want to be able to use voltage division. That would be fantastic, but in order to do that I need to combine negative J5 and 4 in parallel. So I've got negative J5 in parallel with 4. That's negative J5 times 4 over 4 minus J5, which is equal to 2.439 minus J1.951. V2 phasor then is going to be 1. That's the resistor I care about, or the impedance I care about. 1 over 1 plus J4 plus 2.439 minus J1.951 times the input voltage, which is 10 angle 0 degrees, which is equal to 2.498 angle negative 30.79 degrees, which, if I convert back to the time domain, V2 of t is equal to 2.498 cosine of 2t minus 30.79 degrees volts. Alrighty, the next thing I want to do is I want to find V3 of t by turning off all but the current source. Okay, so when I turn off all but the current source, that one is 2 sine of 5t. First thing I would do is I would convert this to cosine by making this 2 cosine of 5t minus 90 degrees, which in phasor land, which is 2 angle negative 90 degrees amps. And then I've got the following. I've got my inductor, which is 2 henries, becomes J times 2 times 5, which is equal to J10 ohms, and my 0.1 farad in capacitor is 1 over J times 5 times 0.1, or in other words, negative J2. So if I draw this circuit out, it looks like this. I've got an inductor, J10, in parallel with this current source, which is 2 angle negative 90 degrees, which is then, I've got a V3 in phasor form here, that's 1 ohm, a capacitor here, which is negative J2, and a resistor here, which is 4. I'd like to use a source transform, so I'd like to convert this to a voltage source with series resistor, so 2 angle negative 90 degrees multiplied by J10, which is equal to 10 angle 90 degrees times 2 angle minus 90 degrees. Negative 90, this is equal to 20. Let's make sure we can do this. Let's redraw that. I've got a voltage source here, which is just 20 volts. I've got J10. I've got a 1 ohm with my V3 in phasor form. I've got nice happy little minus J2. And then I've got a 4. First thing I want to do is I want to combine minus J2 and 4 in parallel. That's going to give me 0.8 minus J1.6. The next thing I want to do then is use voltage division. So I know that V3 phasor is equal to 1 over 1 plus J10 plus 0.8 minus J1.6 times 20. If I plug this in, I'm going to get 2.328 angle negative 77.9 degrees volts, which if I convert back into the time domain is 2.328 cosine of, in this case I had 5 as my frequency here. So cosine of 5t minus 77.9 degrees volts. Now, that's equal to V3 of t. So my total V of t is the sum of my V's, which is equal to, I came up with, let's go back to each of the subsequent parts, minus 1. So let's start with that. It's equal to minus 1 plus 2.5, roughly, cosine of 2t with an angle negative 30.8 degrees plus 2.33 cosine 5t with an angle negative 77.9 degrees volts. This is the total output voltage. If you had multiplied or added those phasors together, you would get a single sinusoid back, and that is bananas. Each of the frequencies for each of these sources needs to be represented in the final signal. And so if you would plot this signal, you would see that happen. All right, that's all I have for this video. Thanks again for watching.